Hello, buenos dias. Today I'm doing a quick presentation on an earthquake that struck the Antofagasta region of Chile in 1995. This happened a few weeks after I was born and in a part of the world I'd really like to visit. So, let me show you. This is just a quick breakdown of what I'm going to talk about in this video. On the right here you can see a satellite image of Chile. It's on the western coast of South America. And just offshore from that, you can see that big black line. That's an oceanic trench, which lies above a subduction zone. So in a little bit, you'll see what that's all about. As I said, this earthquake happened in Chile, specifically in the Antofagasta region, which contains the Antofagasta province, which contains Antofagasta city, which is pictured here on the right. So most of the images in this presentation are from the city, but it's important to understand this earthquake was felt all over the region and indeed in neighboring countries, and it even had some effects that reached across the ocean. Here's another view of the city, so you can see the wide open expanse of the Pacific Ocean in the distance there. The city itself is obviously a port city, it's right on the coast. And then on the right here you can see the ground start to rise up into the foothills of the Andes. In the foreground here, where the photographer was standing, that's the beginning of the Atacama Desert, which is one of the driest places on Earth. This is a cross-sectional view of the crust underlying the Antofagasta region. So, what we see here are two tectonic plates colliding. On the left, this green section with this sort of orangey crust on top, that's an oceanic plate. That's relatively thin. It's made of basalt, which is a dense volcanic rock, and this underlies the Pacific Ocean, or a portion of the Pacific Ocean. The Pacific Ocean is so large that there are multiple tectonic plates underneath it, and one of them is this, the Nazca Plate. So it's coming in from the west, and it's being deflected and diving down underneath this other plate. This is the South American Plate. It's made of continental crust. And in the interface where these two plates meet, you can see what are labeled as accretionary wedge sediments. So those are sediments that were on the seafloor, and they've been scraped off the top of the Nazca Plate as it dives underneath the South American Plate. In that same area is that really deep oceanic trench that I mentioned earlier. Going back to the satellite view, the actual city of Antofagasta is down here. The epicenter of the 1995 earthquake was a bit to the north. There it is, and on this diagram we can see seismic waves that radiated out from the epicenter in all directions. Here are some basic statistics about this earthquake. It happened at 1:11 AM precisely on Sunday the 30th of July, 1995. The modified Mercalli intensity, so this is based on eyewitness reports of what people felt, was rated as severe. So everyone in the region felt some degree of shaking, and there was quite a bit of structural damage. The focal depth was 46 kilometers, so that means 46 kilometers beneath this epicenter is where the earthquake actually started, where rocks began sliding against each other. The Richter magnitude was 8.0, which is pretty large. That's a lot of energy being released. It produced a PGA, a peak ground acceleration, of 0.29 g. Now g is the acceleration due to gravity, so 0.29 g seems like a small number, but it's actually pretty substantial. It's equivalent to experiencing a force that's more than a quarter of your weight. In addition to that, this earthquake also produced a tsunami. In case you don't know what a tsunami is, it's a fast-moving, very powerful wave that often spreads across an entire ocean. And what happens is, as it approaches another landmass, it slows down, sort of piles up on itself, and rapidly increases in height to several meters or more. In this case, the tsunami reached French Polynesia after 10 hours of travel, and when it got there, it reached 2.5 meters high, so higher than a person, which caused a bit of flooding and a bit of damage all the way over there. These are screenshots taken from a news broadcast that you can find on YouTube. I'll include a link to it in the video description below. So we can see some of the damage that occurred in Chile as a result of this earthquake. Close to the epicenter, of course, clocks stopped. Interesting that these two clocks on the same tower stopped about a minute apart. I'm not really sure why that happened. So you can see buildings like this where there are empty rooms and they've just had walls come completely down, collapse onto the street. Just piles of rubble all over the place, roofs caving in or starting to cave in. This last picture was taken standing on a highway, so the highway was actually split in half, and then the two halves moved half a meter relative to each other vertically. Half a meter might not sound like much at first, but when you're in a car, that is impossible to traverse. So a lot of roads and motorways had to be shut down because the earthquake just made them unusable. A summary of the social and economic impacts looks like this. Tragically, 3 people did lose their lives as a result of the earthquake. About 60 people were injured, mostly by falling debris, and about 10 times that number were left homeless. In terms of economic impacts, as I've already said, dozens of buildings were destroyed and major roads were disrupted. In total, there was an estimated 1.8 million US dollars in damages. That's including the tsunami that hit French Polynesia. This is all bad news and it looks pretty bad, but for an earthquake of this magnitude, 8.0 is a very high Richter magnitude, and considering what usually happens in subduction zone earthquakes in South America, this is actually not that bad. For comparison, you could look up the 1960 earthquake that hit Valdivia, which is south of here. That was one of the largest earthquakes ever recorded, and it happened on the same subduction zone. But the impacts from that, both social and economic, were many times worse. Now, the main reason I'm interested in this earthquake is because of the Senka 95 project. And from what I understand, it was initially the Senka 94 project, because before this earthquake, they just happened to be interested in the subduction zone beneath the Antofagasta region, so a big network of seismometers was set up, several dozen of these instruments, to record small to moderate earthquakes. They weren't expecting something this big to happen while the experiment was running, but it did. So all those seismometers were gathered up and they were redistributed because following what's called the main shock in July 1995, scientists knew that there would be a long series of aftershocks. When an earthquake happens, that big event is called the main shock. It represents a movement along a fault underground where rocks are slipping against each other, and they're doing that to relieve stress. However, not all the stress is released in the main shock, usually. So, aftershocks happen, which have a smaller magnitude, but they just release the rest of that stress a little bit at a time. So geologists knew that there would be a long series of aftershocks after the July 1995 event, and they redistributed their seismometers to capture those aftershocks, to capture the signals from them, and try to work out something about the fault that was producing all these earthquakes. In addition to seismometers on land, there were also a bunch of hydrophones, or ocean bottom seismometers, which were placed out at sea. This map here on the left shows the distribution of seismometers as triangles, and the big circles out at sea are those ocean bottom seismometers, or hydrophones. The other circles represent the epicenters of aftershocks, and this big target here, that was the epicenter of the main shock that I showed you earlier. By studying when and where the aftershocks occurred and looking at their distribution using this dense network of instrumentation, scientists were able to reveal the structure of the subduction zone itself. So the interface between those two tectonic plates is the fault. That's where all these aftershocks and where the main shock occurred. What we see here is all the aftershocks plotted against depth. And what we see here basically is the subduction zone. It has a very definite slope. You can see it's sloping down toward the east, just as I showed in this diagram. This other box is what you'd see if you were underground looking out to sea, out towards the west. So it's basically showing the front of the subduction zone, or the front of that diving Nazca plate. from studies like this, we now know that the surface of that plate is actually very rough. It's not smooth as I showed on my diagram. It's full of ridges and canyons and ancient seamounts which are all diving underneath the South American plate. And all of those features give the fault a very complex geometry. It's not all sliding down at the same rate. Some parts of the fault are locked. They cannot move relative to each other, and so there's a lot of stress building up there. This makes it difficult to, let's say, predict an earthquake on the fault. I mean, you can never predict an earthquake, but it's especially hard when they happen on faults with complex geometry. However, these studies have helped geologists around the world to recognize that fault geometry really matters in controlling earthquakes, in how big they can get and where they can occur. And it's also helped us to recognize why different faults show different behaviors. Well, thank you for watching. I hope you enjoyed this quick presentation. I've just got a list here of all the references I used, including that news report. If you have any questions or you'd like to know more, please let me know in the comments section below, and feel free to request a topic for a future video. Thanks again, and good luck with your study.